Hi everybody, welcome to another video in the Swiss Math section 6.5. So in this section we'll study about permutation and combination of other unique situation. And once again, permutation where order does matter and combination order does not matter. Right. Now, the first case we want to study is the permutation with repetition. So the number of permutation of set of n objects with repetition allowed is n to the r. So in this case, that's simple enough. One example is good enough to see why the formula works that way. How many strings of length r can be formed using the uppercase letters of the English alphabet? So there are 26 English letters. And then the string of length r, so just 26 to the r power. So pretty much on the first letter we can choose any of the 26, the second one any of the 26, and we choose that r time. So that is 26 to the r power. Very straightforward, right? Because repetition is allowed. If repetition is not allowed, so that's the normal permutation, then we have 26 times 25 times 24 and so on, right? But repetition is allowed, so we can have that. Right. Next, the combination with repetition. Now this is a lot more interesting, a lot more difficult too, but the solution is kind of genius idea of that. So combination with repetition, and this is in the book it's called the star and bars method. Star and bar. I prefer to use this dash and dot or dot and dash method. It doesn't matter. Right, so let's look at the problem and see what we're dealing with here. How many ways are there to select 5 bills? So we select 5 bills from a box contain a bunch of bills. So you have the whole box of $1 bill, a box of 2, box of 5, box of 20, 50, and 100. Right. So the idea is we can select, if you want to, we select 5 bills out of those, right? If you want to, you can select all 5 of the $1 bill, and we're done with it. Or just all 5 of $100 bills, and we're done with it. Alright, now here's the situation. Let's just say just try to draw the box of cash. So $1 bill separate by, there's a 2, a 5, 10, 20, 50, and 100. How would we choose? By the way, let's say, okay, you choose all 5 $1 bills, so we just say, and for that I use a star to denote a dollar bill here, like 1, 2, 3, 4, and $5 bill. And after that I draw a dash, and there's nothing in between. So 1, 2, 3, 4, 5, 6. So 5 of them is between star 5 bills of 1, and then the dash, between the dash or between the bars, they're empty. 1, 2, 1, 2, 3, 4, 5, 6. So that is represent $5 $1 bill. Right. Now let's look at another scenarios. Let's say if you want one of each. 1, 2, 3, 4, 5, 6, 7. That's too much. Let's say you don't like the $2 bills and you don't like the $100 bill. You want one of each. 1, 5, 10, 20, 50. So represent by 1 star for dollar bill, separate by 2, there's nothing to choose 2, so just skip it. And then you choose one $5 bill, a star. And then a bar, 1 for 10, a bar, 20, a bar, and 50, a bar, and for 100, skip, nothing here. Alright, so as you see, this is the case where we have a dollar bill, 1, a 5, a 10, a 20, and a 50, 1 each, represent by this. As you see, doesn't matter how we represent it, the number of stars and the number of bars add up equal to the number of we have to select, 5, and the number of choices we have, 7 minus 1, right? Remember, because there's 7 of them, but we have to select the bars in between, so there's only 1 less, right? So 5 fingers between them, there's only 4 dividers, if you will. So in that case, we have, this case, 5 stars and 6 bars, or usually, or sometimes I say it, 5 dots and 6 dashes, 6 dashes and 5 dots. Right, now we just need to find a way to rearrange them, so it will be easy, right? So bottom line is there's 11 objects in total. We're just gonna distribute and choose some particular order, and we have 5 stars. Just choose where we want the star to be at. The bar will fill out the rest. It's either C11 5 or C11 6. That's the Pascal identity. But so will be this. So 11. Pick 5. 462. Right? Remember, the number of stars and the number of bars equal to how many we choose. From how many choices do we have? Minus 1. How many we have to choose? What are the options? So the choice, the number of choice plus the number of options, minus 1. So here, in theorem, we said the number of combination with repetition are allowed is equal to the C n plus r minus 1. So in this case, n is the number of options. R is the number we have to choose. Like this case, we choose 5 bills. So number of time we have to choose. So that, don't forget, there's a minus 1. Right, next. How many solutions does equation x1 plus x2 plus x3 equal to 11? Right. So, how do we say that? So we have the x1 plus x2 plus x3 have to be equal to 11. Now, that means we have to choose some in x1, some in x2. Oh, by the way, how many solutions does this have? Provided if x1, x2, x3 have to be integers, maybe whole numbers. Of course, if you have like 1.5, 2.3, and then of course there will be infinitely many solutions for sure. But we want this to be positive, I should say non-negative integers. Non-negative integers. So it could be 0, 1, 2, 3, 4, up the way to 11. Right. So, in that case, you put a bar in. You can choose sum of x1, and then you run a dash or a bar, and then we choose sum of x2, and then we choose sum of x3. So that all together add up equal to 11. So in this case, there are 11 number we have to choose. For example, if we have the solution of 2, 3, and 5, 4, and 6, for example, that add up to 11. So that means we have to have 2 star for x1, a bar, 3 star for x2, another bar, and then 6 star. So in that case we have 11 star and 2 bars, so 13 in total. And so the way with this is we have 13 in total, and we have to choose how many star do we have. That will be 11 or 2 pretty much. Sorry. Actually that's 11. So 13 math, 11 78. So that is where we want the star to be, or where we want the bar to be. This case we only have 3 options. So if we have n minus 1, that is 2. So either C13 of 2 or C of course you can also use 3, 13 and 2. We have 3 choices. The number of options could be x1, x2, x3. We take the number of options minus 1, and that is this number. Either way we have that. So we just put how many stars do we have and how many dash bar will we have. Either way, that is the right answer. So we need to determine how many bars we have and how many stars we have, and then we find a combination. Right. Next, suppose that the cookie shop has 4 different kinds of cookies. How many different ways can 6 cookies be chosen? So there are 4 different kinds of cookies. Let's see, A, B, C, and D. And in that case, there are 3 bars to divide 4 choices, right? Yeah. 3 bars to divide the option that we choose. We can choose one of the 4 type of cookies. So there's 3 bars, and we have to select 6 cookies. So in that case, just pick one. For example, 3 of the first, 2 on the second, and 1 on the third, and none of the last. So that's how we have. So 6 stars because we're going to choose 6 cookies, and there are 3 bars because that to divide 3 options. 4 options we have 3 bars, divide 4 options. So we said 6 stars and 3 bars. So this we have combination of 9 objects total, and either 3 or 6 doesn't matter. Either 3 bars or 6 stars doesn't matter. C9 3 or C9 6. We said 9 2 3. Right, 84. So that is a combination where repetition is allowed. Next, permutation, meaning order does matter within distinguishable object. So of course when you select an object out, some of them might be exactly the same. So in that case it doesn't make really different. So how many different ways, how many different strings can be made by reordering the word success? Let's see how many words it is. 1 2 3 4 5 6 7. Alright, 7 in total. If we want the combination permutation 7 out of 7, that is of course 7 for the first part, 6 5 3 2 1. So that is 7 factorial. We don't need to know what it is. Right, 50, 40. Now, but that, of course, we assume that all the letters are the same. So we start with that. Having said that, here we have 3s. The s are the same when it's scrambled. It doesn't really count the different permutation, right? Because the s, if you switch this s with that s, that's still the same. So we have to divide by 3s. 3 factorial, because the 3s can scramble. We overcount it. We have to divide by those. And then 2c interchange, we have to divide by 2, because cc or cc is still the same. So we have to whatever we have to divide by 2, and then 1u and 1e. That's fine. You can just say 1 factorial for u and 1 factorial for e. That's fine, because 1 factorial is 1. We can just put 1 factorial there without any problem. Right. So bottom line is we start with that. Uh, 50, 40 on the top. 3 factorial. 2 factorial. Then 1, we really don't need it. Right, 420. So this is permutation with indistinguishable objects. Like how many of those we can just divide by those factorial, because this 3 here is actually 3 permutation of 3 out of 3. So if we choose 3 objects, scramble in 3 position, that is 3 factorial. Right. So bottom line is the permutation of indistinguishable object given by this formula, and n1, n2, and k, how many kinds we have. Right, another example here. How many different passwords can be made using all of the letters in the word Mississippi? So let's just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 letters. Let's count. I, 1, 2, 3, 4, 4i. S, 1, 2, 3, 4. P, 2. And then an M. 1M. So there are 11. So how many, if we scramble this, there's 11 letters total. But then all the I interchange, we have to encounter that. So that's 4 factorial. And 4s, and 2p, and 1 for m. Right? So pretty much that. $11 factorial. With 4 factorial. 4 factorial. 2 factorial. One factorial. We don't really need to put it, but it doesn't hurt if we do. Alright, so 24,650. So how many digits, how many choice we have total over how many repeated, and we have factorial for each kind. So that is permutation with indistinguishable objects. And next I'm just going to put this in writing so you can read that. So distributed object into boxes. Many problems can be, different scenario can be considered here. Many counting problem involve distributed object into boxes. The object might be different, the boxes might be different or identical. So we have 4 different scenarios here. So we might have the distinguishable object over distinguishable boxes, or indistinguishable object into distinguishable boxes, and then so different scenarios. There will be each one we have to do case by case and have to do a reasoning for each case. I'm just going to put that here to complete the section. But with that, we finish section 6.5. Thank you for watching, and see you in another video in Discrete Math.